Hello everyone, we are in the third session of the chapter kinetic theory. In this session, first we'll learn what is a degrees of freedom is. We know that in a gas, the molecule can have a random motion. They can move in a straight line path, they can have a rotation, they can have a vibrational motion also. For every rotational motion, for every translational motion, they possess a translational kinetic energy of half mv square. For rotational motion, they possess a rotational kinetic energy of half I omega square. And for vibrational motion, they possess both kinetic and potential energies of half mv square and half kx square respectively. If you want to understand this degrees of freedom, let us consider a gas molecule which is having its motion only along one direction, either in x direction, y direction or z direction. We say that that particle can have an energy only in one direction, means it is having only 1 degree of freedom. Suppose the same particle is having a freedom to move in two coordinates, x and y coordinate, or x and z, or y and z. Therefore, we say that the particle is having 2 degrees of freedom. If that molecule is having a freedom to move in all possible directions, x, y, z, in a space, then we say that that particle has 3 degrees of freedom. So, if we define the degrees of freedom, a degrees of freedom is nothing but the total number of independent ways an object can possess energy. Or we also define the degrees of freedom as the total number of independent coordinates needed to specify the position of a system. So this is called as a degrees of freedom. Now, for a monoatomic gas means a molecule of a gas is having only one atom. For example, argon, neon, etc. So that molecule is having one atom in it, and that molecule can have a translational motion in all the direction. They can move in x-axis, y-axis or z-axis. Therefore, it possesses 3 degrees of freedom due to the translation. But that molecule is having a rotation, but that rotation can be negligible because its size is very small. Therefore, a monoatomic gas possesses only 3 degrees of freedom due to the translation. So, the degrees of freedom for a diatomic gas, for example, oxygen. We know that oxygen is a diatomic gas, and in diatomic gases, what happens is, suppose if this is the diagram to explain this, if we have a molecule like this, it is having two atoms in it. So that molecule can have a 3 degrees of freedom due to translation, because the molecule can have a freedom to move in all possible direction. That is why it possesses 3 degrees of freedom due to translation. But when it comes to the rotation, it can rotate about the x-axis, it can rotate about y-axis, or it can rotate about the z-axis as shown in this diagram. But this rotation is negligible compared to these two. So here the rotation about the y-axis and z-axis is considered, but this is neglected. The axis which is along the line joining of the two atoms. So this rotation is neglected. That is why due to the rotation it possesses only 2 degrees of freedom. Therefore, the total number of degrees of freedom for a diatomic gas will be 5, 3 due to the translation and 2 due to the rotation. Now, if we consider a degrees of freedom for a non-linear triatomic gas molecule, carbon dioxide you can say. So in this, what happens is, it can have 3 degrees of freedom due to translation, because every gas molecule will be having a 3 degrees of freedom due to translation, because it is having a freedom to move in all the directions. But for this molecule, it can have a rotation about x-axis, y-axis or z-axis. The molecule can rotate about x-axis, y-axis and z-axis. Now the 3 rotations can be considered. Therefore, a non-linear triatomic gas molecule can possess 6 degrees of freedom. Now, what does this law of equipartition of energy says? Law of equipartition of energy says that the total energy of the system is equally distributed among its various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kT. So this law of equipartition of energy gives the how the energy is going to distribute among the various degrees of freedom in equilibrium. So we know that a gas in a container possess some internal energy because of the motion of all those molecules. They possess internal energy. So due to that internal energy of the system is equally distributed among its various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kT. Suppose if we consider a monatomic gas. So for a monatomic gas, we know that the degrees of freedom is equal to 3, which means the total internal energy of that system is equally distributed in 3 ways. Okay, that is what the law of equipartition of energy says about. Now, the total energy of the system. So how do we calculate the total energy of the system of that gas? Now, for this, we consider n number of molecules and f degrees of freedom. The total internal energy associated with it is given by. We know that from law of equipartition of energy, the internal energy is equally distributed among the various degrees of freedom. Per 1 degree of freedom per molecule, the energy is half kT, where k is a Boltzmann constant. We know that. Now, for n molecules and f degrees of freedom, this is for 1 molecule per 1 degree of freedom. Half kT is for 1 molecule and 1 degree of freedom. So for n number of molecules and f degrees of freedom, internal energy is given by n into f into half kT. Now for 1 mole of a gas, n is equal to Na, which is nothing but an Avogadro number. So if you multiply n with Kb, so Na with Kb, so this gives the R. R is nothing but a universal gas constant. So this has been explained earlier. So Avogadro number multiplied by Boltzmann constant gives us R. Therefore, U is equal to F into half into R into T. So this equation gives the total internal energy associated with 1 mole of a gas at a temperature T. Now, so what is the application of this law of equipartition of energy? So where do we apply this in order to find the molar heat capacities of the gases? So what do we mean by this molar heat capacity of a gas? Suppose we consider 1 mole of a gas. If we consider 1 mole of a gas, the amount of heat required to rise the temperature of 1 mole of a gas by 1 Kelvin is called as molar heat capacity. Okay, so amount of heat energy required to rise the temperature of 1 mole of a gas by 1 Kelvin is called as molar heat capacity of the gas. But this molar heat capacity of the gas, while heating, the pressure of a gas may change or volume of a gas may change. That is why one quantity is always held constant here. See, the molar heat capacity of a gas at constant volume is given by Cv is equal to du by dt. So what do we mean by this? The molar heat capacity of a gas is calculated by remaining the volume of the gas constant. Therefore, Cv is equal to du by dt. This U is nothing but the internal energy of the system. And how do we define Cp? It is the molar heat capacity of a gas at constant pressure. So this is given by R plus Cv. Now, using the law of equipartition of energy, let us find out the molar heat capacity of a monoatomic gas first. So Cv and Cp are the molar heat capacities of the gas at constant volume and pressure respectively. Now we need to find the same for the monoatomic gas. So the number of degrees of freedom for a monoatomic gas is 3. We know this already. The energy associated with 1 mole of a gas is given by. So for 1 mole of a monoatomic gas, let us consider the 1 mole of a monoatomic gas, which is given by U is equal to F into half RT. So this is obtained by this equation. So F into half into R into T. Now for monatomic gas, F is equal to 3. Therefore U becomes 3 by 2 RT. You just substitute F by 3. So 3 by 2 RT. Now we know that Cv is equal to du by dt. So you need to differentiate this 3 by 2 RT now. So Cv is equal to du by dt. d by dt of u is nothing but 3 by 2 RT. Now take 3 by 2 R outside. So we get dt by dt. This is also capital T. Therefore dt and dt gets cancelled. We get Cv is equal to 3 by 2 R. And the molar heat capacity at constant pressure is given by Cp is equal to R plus Cv. Substitute this Cv by 3 by 2 R here. So R plus 3 by 2 R gives us 5 by 2 R. So Cp is equal to 5 by 2 R. Now if we take the ratio of them, the ratio of Cp to Cv. The ratio of Cp to Cv is known as gamma. So gamma is equal to Cp by Cv. So 5R by 2 by 3R by 2. R by 2 R by 2 gets cancelled. So 5 by 3 is equal to 1.67. Therefore, using the law of equipartition of energy, first we find the molar heat capacity of a gas at constant volume and then at constant pressure. By taking the ratio of these two, we get gamma as 1.67, which is a constant. You need to remember this. Okay, gamma is equal to 1.67. Next, the molar heat capacity of a diatomic gas. So I have not done in detail here. So for a diatomic gas, we know that F is equal to 5. So we have to use the same steps here only. First, you will take this U is equal to F into half into R into T. For diatomic gas, take F is equal to 5 and then do this calculation to obtain the values of Cv and Cp. So by that, the value of Cv will be 5 by 2R, Cp will be 7 by 2R. If you take the ratio of Cp to Cv, then gamma is equal to 7 by 5, which is equal to 1.4. So for a diatomic gas, the ratio of molar heat capacities Cp by Cv will be equal to 1.4 or it is 7 by 5. Next, in the same way we have done for the non-linear triatomic gas. So for that, gamma is found to be 1.33. So you just remember the values of gamma for monatomic, diatomic and non-linear triatomic gases. And you need to remember the degrees of freedom for each of them. Then you can easily derive this. Fine. We'll move on to the next one. Now for a polyatomic gases means more than 3 or 4. So then what or how to calculate the molar heat capacity or the ratio of molar heat capacity. So for a polyatomic gas molecule, it should consist of 3 translational degrees of freedom. It should possess 3 translational degrees of freedom and 3 rotational degrees of freedom and a certain number of vibrational modes also. So that is taken as F here. Now the total energy of 1 mole of a polyatomic gas is given by U is equal to 3 by 2 RT plus 3 by 2 RT. So this is due to the translation, this is due to the rotation and this is due to the vibration, F into R into T. RT is common, take that RT outside, 3 by 2 plus 3 by 2 plus F. 3 by 2 plus 3 by 2 becomes 3 plus F into R into T. Now if you take Cv is du by dt. So if you do du by dt for this, you will get 3 plus F into R. And Cp is R plus Cv, and if you substitute that, you will get 4 plus F into R. Then the ratio of Cp to Cv is called as gamma for a polyatomic gas. So gamma is equal to 4 plus F into R divided by 3 plus F into R. So this gives the ratio of, or gamma is equal to 4 plus F divided by 3 plus F. So this gives the ratio of molar heat capacities for a polyatomic gases, where F is the number of vibrational modes. So this is the general equation for the ratio of molar heat capacity of the polyatomic gases, 4 plus F by 3 plus F. Now very important one, the molar heat capacity of a solid. So how to take for a solid? See, solid is different from the gases, correct? In a solid, the molecular arrangement is compact. So due to that compact arrangement, the molecules cannot have a translational motion. they cannot possess a translational or vibrational motion. They cannot possess a translational or rotational motion. They can only possess the vibrational modes of energy. That is why they are free to vibrate about the any three directions. A molecule inside a solid can have a vibrational motion in all the three directions. Therefore, each mode of vibration possesses an energy of K into T or Kb into T, where Kb is again a Boltzmann constant. Now it is not half kT, but instead it is K into T. So each mode of vibration possesses K into T, but inside a solid, the molecule can have three modes of vibration. Therefore, for 1 mole of a solid, the total energy becomes 3 into R into T. Okay, fine. Next, C is the molar heat capacity of a solid for 1 mole of a gas, 1 mole of a solid. Then C is equal to du by dt. So d by dt of u is 3RT, and take 3R outside, dt by dt, this is also capital T, I told you already. So dt by dt gets cancelled, so we get C is equal to 3R. So this is an important result. So for a solid, the molar heat capacity is equal to 3 times the universal gas constant. C is equal to 3R. So remember this. This is very important for you. Next, in the same way, we can calculate the molar heat capacity of water. So water is treated like a solid. So in every molecule of a solid, it has 3 atoms in it, and the average energy of each atom is 3 kT. So for one atom of a water molecule, so it is possessing an energy of 3 kT. So it has 3 atoms in a molecule, so 3 into 3, 9. So 9 RT. So 9 RT is the total energy associated with each molecule of a water. Then C, again we calculate the molar heat capacity of water by finding du by dt. So d by dt of 9 RT, so it becomes 9R. So the molar heat capacity of water is 9R. So you should remember these two. For a solid, it is 3R. For any solid, C is equal to 3R, and for water, C will be equal to 9R. Fine. So now the last concept is mean free path. So what do we mean by this mean free path? We know that in a gas, the molecules are under random motion. While moving, if it is undergoing a collision with one molecule, then in order to undergo the next collision, it moves certain distance. Correct? Means in between the two collisions, it is traveling some distance without colliding with any other particles. So that path or that distance traveled by a molecule of a gas without undergoing any collision is called as a free path. That is called as a free path. If that molecule is undergoing the collision with so many collisions, it will not travel the same distance between the two successive collisions for different types of collisions. Correct? Means if the molecule has started its motion, it is undergoing collision with a molecule 2, and it is freely moved up to certain distance, then it undergoes the collision with molecule 3. It has traveled some distance d1, then it is traveling again some distance and undergoes a collision with molecule 4. It has traveled a distance d2, then it undergoes a collision with fifth molecule. It is traveling a distance of d3. Means that d1, d2, d3 may not be same. So it cannot travel the same distance between the two successive collisions. That is why what we are going to do is we are going to take an average of that. So the average distance traveled by a gas molecule between any two successive collisions is called as a mean free path. So you should remember what is the mean free path. Mean free path is the average distance traveled by a gas molecule between any two successive collisions. Now, in order to derive this, we'll have this diagram. If you can observe the diagram here, this is a molecule A, this is a B and C. Initially we thought that B and C are at rest and only A is moving. So this A, the molecule A, is having a diameter of D, or the distance between any two, the distance between the centers of any two molecules is equal to D here. And imagine this A is moving in this direction. The molecule is moving in this direction by traveling a length of L through this cylindrical shape. Now, to find out the mean free path, lambda is represented. So lambda is equal to, how to find the lambda? Total distance traveled divided by number of collisions suffered. So total distance traveled divided by number of collisions suffered is called as a mean free path here. To find the number of collisions suffered, how do we calculate this? If this molecule is moving from here to here, means it has to travel a distance of L, and if we calculate the number density of molecules here, number density means number of molecules present per unit volume of this cylinder into volume of cylinder, that gives the total number of molecules present in this cylinder. So this has to undergo collision with each molecule of this cylinder. That is why the number of collisions suffered will be equal to number density into volume of the cylinder. Number density into volume gives the total number of collisions, or total number of molecules in that. So we write this number of collisions suffered is, number density is N, and volume of the cylinder is pi d square L. D is the diameter, sorry, the D is the radius of the cylinder, and L is the length of the cylinder. Therefore this is pi d square L. So lambda is equal to L. So total distance traveled is equal to L, because while moving from here to here, it has to travel a distance of L. So this is L divided by N pi d square L. So if we cancel this, lambda will be 1 by N pi d square. So this equation gives the equation for a mean free path, but this value is not exact, as we have considered this molecule is only moving and these two molecules are not moving. But practically all the molecules are under some kind of motion. So we have to correct this equation by taking root 2 in the denominator. So we get lambda is equal to 1 divided by root 2 n into pi d square. So this gives the equation of a mean free path. So what are the terms here? Lambda is called as a mean free path. N is the number density of that gas molecule. D is the diameter of the gas molecule. Okay, so this equation gives us the equation for a mean free path of a gas molecule. Fine. So this is the end of the session as well as the chapter. In the next chapter, we will discuss some more concepts. Thank you.